start with this section, and it's not terrible. You're doing the exact same thing we have been working on. It just adds an extra, basically 2 steps. And then we've got some review stuff to look at and go from there. Tomorrow we will quiz, like I said, over these first 2 sections. It does not take very long to get through these, so I don't anticipate it being very off the bat or anything like that. Then on Wednesday, we're going to jump into trigonometry. And what we do at trig is that I've realized now by kind of going through a lot of the problems and whatnot, is that our textbook is pretty crappy when it comes to the way it presents and goes through trig. This textbook is written in such a way that it assumes that you guys have already gone through it and yet probably pseudo have mastered it, which you have. So, and I don't mean that jokingly or anything. What I'm saying is that we have a bunch of stuff to get through with it to get going. So we probably won't be using really anything on the textbook to go through there. It's a lot of worksheet stuff that I've made and worked through and built up and stuff. It is super important to always have a calculator with you from here on out. The 45s and stuff like that, you can kind of get away with it, but trig you cannot do without a calculator. You have to have that. So I think we've gotten to the point where we've kind of figured that out. Trig, I think in the textbook it's like 3 sections worth, but we'll be doing it for the better part of 10 days or so to finish it out. It takes that long to get through everything and go from there. Okay? Just so you guys know where we're at. Excuse me. So, one of the things that happens that I've noticed throughout the past couple of class periods and when we're doing stuff is that you guys have a tendency to not believe me when I say to write this out the way that I do.
It's easy.
Good. Now, what happens a lot of times, the reason that I was saying to use these arrows, because it tells you what the angle is looking at. It's looking at a side across from it. It's looking at a side length that is x times the square root of 3. Well, that side length might equal 7. And you'd have to figure out the rest of it from there. So the idea of using the arrows and drawing them across, it helps you to identify it. It doesn't mean that the side it doesn't say that x is that. It's saying that this 60 is looking at a side length of 9. Very good. You have to figure out what that factor is being multiplied by the square root of 3 to get you to 9. Okay. So you set up after we put away our phone.
Do you want some of my tissues?
I'm not laughing at you. Just the randomness of I zippered my. No, I understand having tissues. You're probably all full of boogers, so that's fine. It's a snot day.
No, I didn't. I had it.
I'm joking. Anyway, yeah. So Joe was saying to do this. Now, when you type that into the calculator, you get an answer of 3 root 3. Okay. And then that gets represented as a value of x. I write you a pass. No, I have to write you a pass.
No.
Yes, this is really awkward.
I mean, my facial life. Yeah, which I want to understand.
Okay? So remember, the more that you write these out, to help set things up, the easier all of this becomes. I know it takes a minute or two per problem to write everything through, but it forces you to know where things are going to get placed, and it's going to force you how to set up and solve the problem. Okay? With that being said, the style of problem that we haven't really talked about yet is when you have 2 triangles put together. ladies and gentlemen, I really don't want to talk over you. One of the things that we haven't done yet is that we haven't done the problems that you have multiple triangles with. And when we're doing these, we're going to have special right triangles next to each other. They're going to have a shared side. They might be two different triangles. They might be the same and just rotated through. Yes, ma'am? No, this is still the same stuff we've been doing. Yeah, this is just the last little bit of technically 8.2, but I don't. Remember, a lot of the stuff that we're doing, like especially if you get into trig, I'm not going by any sections. It's just trig.
What up, trig?
Anyway, so when you get to a problem like this, guys, I only dropped it 3 times this whole year. How many times do I do this in a day? All the time. So, first thing you have to do when you get to this. First thing you have to do when you get to one like these. Figure out what side length or what angle do you know across from. In this example, what angle do you know across from? Which one do you know for certain? Let's try this again, guys. What number? Guys, let me rephrase this. This should not take this long to figure this out. There should be an argument here. What side length do you know across from an angle? A 60. Okay. I know across from a 60. I'm looking here, and I'm looking at an 8. So I know the side length across from a 60. Which means I'm going to write down the ratios of the sides for a 30, 60, 90. Just like we've done over and over again. Okay. As you go through this, remember, you know across from the angle that is 60 degrees, that 60-degree angle is across from a side length that is equal to 8. I have to solve that one-step algebra problem. How do you solve the one-step algebra problem that has multiplication in it? You undo. You divide both sides by the square root of 3.
Ooh. It's complicated.
Ladies and gentlemen, there's way too much of this. Okay? You're using the calculator. You have a one-step algebra problem. Something times the square root of 3 is 8. How do you undo multiply? You divide. You type in the calculator, 8 divided by the square root of 3. It will tell you then x is 8 root 3 over 3. Okay? Now, instead of writing out, since that's the value of x, instead of substituting it into both across from the 30 and across from the 90, I only have to use one of them, because then that side gets reused into the next triangle. Which one do I have to put that 8 root 3 over 3 in? For across from the 30 or across from the 90? It's across from the 30. The reason that it's across from the 30 is, remember, this is the value of x. There's my 30, which gets me to the other triangle. You're trying to figure out where do I place it so that way it gets to the other triangle. And now it's across from a 45. Bless you. What's that? We do, because now it's across from a 45. So both across from both 45-degree angles is that value of 8 root 3 over 3. But that doesn't help me get to my answer. I need to be across from the 90, so I'd have 8 root 3 over 3 times the square root of 2. Because it says x times the square root of 2. Do you want the quiz now? Or can you just be quiet for a second so I can try to explain this without everybody interrupting each other so you can understand where this is going from? This should not be happening in this class. You guys are better than this. What's happening here, give me 1 second there. What's happening here is that you use the first triangle to figure out a value to get you to the second triangle. Okay? I know that they're both using that some value of x, if you will. It doesn't necessarily mean that this is always going to be the same value for all the way through, so you have to reuse it. Okay? When we got to this part here, knowing that across from our 60 was 8, we threw it into our algebra jig, divided by the square root of 3, that gave us an x value of 8 root 3 over 3. Which meant that everywhere we saw an x in the 30, 60, 90, we would put 8 root 3 over 3. Of those side lengths, I don't need to use this one because it's not part of the second triangle. That's why I didn't bother substituting in across from the 90. All I did was substitute it across from the 30. That side then goes to a 45, 45, 90 triangle. And like you were saying, it is that value of x because they're both the same. This is going to equal 8 root 3 over 3 times the square root of 2 then, because I'm using my scenario. Sir? Yeah. It depends on what side you know. I don't know in that triangle, I don't have anything across from the 90. Remember, when you have these two triangles, if I have a 45, 45, 90 triangle, and this side is 8, we just use an 8, let's use 4. Okay. When I write this out, it depends on what side you know to what you have to do. These are x is equal to 4. Because you're taking this value of x goes right here. Okay. Now, if it was the other way around, if this was 4, then you would have to divide it because you have to figure out what that is. Okay. It's always dependent upon where you're placed. Since if I know that across from the 90 is equal to 4, then I would have to divide by the root 2 to get my answer for x. Whereas if I already knew this was x, then I put it in front. If I don't know what x is, I have to divide it. Yes, ma'am? Yeah. Yeah.
How do we know, like, what time to know?
It's what side length do you know? I know an 8. Where's that 8? 8 is across from a 60. And then I go from there. Now, the other classes I was having, they were having problems trying to type that into the calculator, right? When you have this, this is where things are going to get kind of weird with the calculator. You have to be careful with how you type things. When you have 8 root 3, so we have a fraction, we have 8 root 3 over 3 times square root 2. And it automatically spits it out for you. 8 root 6 over 3. It'll do the work for you. Okay? It'll do the work for you. That's what's great about that calculator. Okay? Now, one of the things that does happen, and I think I have an example myself, I'll talk about that in a little bit. Okay? It's just a matter of seeing where something is placed to figure out where you're going into the next spot. All right, I'll show you another. Start with try this one. Start with this one, please. Give this one a shot. All right. Across from what angle do you know to start? In what kind of a triangle? 30-60 or 45? A 30-60. Okay. So what happens with this one, you can get two different results if you're not careful. And either one of them is correct, but I want to show you a way that makes it so the calculator won't, it won't get all crazy on it. So we know across from a 90, we know across from a 90, 2x. So we know that the side across from the 90 is equal to 7. And you divide that out, it's 3.5, right? Now, if you hit 7 divided by 2 in the calculator, you get 3.5. But watch what happens if you get the fraction 7 over 2. You get 7 over 2. Now, there's a reason why you'd want to use one versus the other. The reason why I would want to use the fraction one here is because if I use the fraction 7 over 2, it'll automatically simplify my radicals for me. Because if I leave the decimal, if I use the 3.5 and I multiply it by the square root of 2, it's going to give me some crummy number. Whereas if I use the fraction of it, I'm just showing an example. I just hit the square root of 2 just for over that. But if I hit 7 over 2 and I multiply it by the square root of 2, it'll simplify the radical. See what I'm saying? So even though it's a half z, make sure you always use the fraction version. Does that make sense?
Yeah.
Stick with the fraction version because it will automatically simplify when you have the radicals with it. It'll do the work. Whereas otherwise it could give you decimals. You don't want that. Okay? So we know that it's going to be 7 over 2. Now, what side length do I have to put this 7 over 2 to get me to the next triangle?
30.
30. Very good. I have to go for the 30 because the 30 is here. So this is looking at a 7 over 2. In that second triangle, that 7 over 2 is now across from which angle? It's across from the 90. It's across from the 90-degree angle. It's the hypotenuse. So I go through my 45, 45, 90. Now I have to divide it by the square root of 2. So in your calculators, if you do, wrong calculator, if I do the fraction bar again, 7 over 2 divided by the square root of 2, it'll automatically clean that up for me. And it gives me a radical answer. Okay? It'll give me the radical answer because I have to divide this by 2, root 2. Okay? And that's where it gets me that 7 root 2 over 4 as a final answer because that's what's across from the 45. Okay? It just looks weird with all those digits and stuff. But remember, it's not any different than the stuff we've been doing. You're just moving yourself from one triangle into the next and going from there. Okay? No, you don't need it. It's which of those two sides are going to help me get to the next triangle.
It wouldn't matter.
What side length did we have to find? We had to find across from I had to find across from a 45. So my answer then would be 7 root 2 over 4. And there's my answer. Or you write it next to it. Somehow tell me what the answer is. No, you need to kind of tell me where the answer is. I don't know what your work was. That's about as goofy as this gets. Now the other stuff that we did was this. Enough. Really. When do I use that? Right triangles.
Isosceles.
Don't need it. I could use it for isosceles, but when I have Pythagorean theorem, I'm solving for missing side lengths. Now, I'm solving for missing side lengths also with the 30, 60, 90, and the 45, 45, 90. But with those, I only need to know one side length, because there's a ratio of the patterns and I can find the other ones. When I have a normal right triangle that is not as special, if I have a regular, a right triangle that doesn't have a special degree measures to it, I have to only be able to use Pythagorean theorem, okay? Because there's nothing to tell me what my angle measures are. I can't assume what they are. So I have to use that. Plus, when you're using Pythagorean theorem, you have to have two side lengths. If you only have one side length, you're using the special, okay? So in this one here, at 8 and the 17, what am I solving for, a hypotenuse or a leg? A leg. And the reason why we're solving for a leg is because which one of those two is a hypotenuse? The long one. Where is the long one located as far as the hypotenuse in the right triangles? Always across the 90. Now the reason why I keep reminding you of that is because when we get to trig, we're always going to ask, do you know the hypotenuse? If you do, you can do certain things. We're going to find this missing side. So you have 8 squared plus something squared is 17 squared. Okay. Now, excuse me, in this case, just pressing buttons now. You wind up with x squared is 225, because you'll take 17 squared, subtract 8 squared, and you get 15. Okay. Pythagorean theorem. Yeah. Yeah, Joe. What's up? Now, the other thing that we did with this is that sometimes we wrote it backwards.
Oh, yeah, we did it greater than 1.
Correct. Very good. The reason that we did this is because depending upon what values were written up, you were able to tell what type of a triangle you had, whether it was right, obtuse, or acute. So we had equal, greater, or less. If it was equal, what kind of a triangle is it? Right. Oh, did you hear? It was a right triangle. They were equal. If the c squared was bigger, it was obtuse. Very good. Yeah, by process of elimination. So you get that. Now remember, excuse me, this is helping us to tell what type of a triangle they have via the angles. It just means you have either a right triangle, an obtuse triangle, or an acute triangle. Right? We always did the c squared first, and the reason we put the c squared first, because then if it was greater, we knew it was obtuse, if it was smaller, it was acute. It was just another way of writing it. We wrote it in reverse that way. I believe we call this the converse of Pythagorean theorem. Now, the other thing that we talked about in this part, in this section, was sometimes you had to use the calculator to figure out what side length was playing the largest role, or the larger side. For example, if I have the numbers 5, square root of 61, and 6. If I type in that calculator square root of 61, it's going to give me an answer of square root of 61. Okay. And if I need to know that whenever we're doing these things, Well, I have to know which side length is the largest, so that way I know that it has to be playing the role of C. What button do I press to get the decimal equivalent? The arrows, very good. The double arrows will give me a decimal equivalent of that. Okay. Now, or your really old calculator will do that as well. So of those three side lengths, the 7, or excuse me, the 5, the 6, and the root 61, which one has to be playing the role of C? Root 61. So you would write this, and this is the other thing we did. What's the relationship to it? 5 squared, 6 squared. There's a reason why I put parentheses around square roots. Not so much of a big problem with this one, but it's a big problem if it was 2 root 3 and I squared it. If you get in the habit of every time you're about to square something that has a squared symbol in it, to put that whole piece in parentheses, you will be less likely to screw up later on. Right? So the square root of 61 squared is 61. 5 squared plus 6 squared is 61. So what kind of a triangle is it? Okay. And again, the reason why I'm telling you put things in parentheses is because that way if you get something that is this, you don't screw it up. Right? Because it is very, very, very easy to screw that up. Other than that, that's pretty much all we had then. That was just special right triangles and working our way through diagrams. Right? Let me give you some problems.
Well, that's too short.
Sorry. I don't remember finding any spirit, that's why. Why count? They'll wind up here eventually. Thank you. Yes, ma'am. What's that? No, let's turn this into our. This won't take long. This is good practice. What's that? It's good for you. Shh, ladies and gentlemen, come on now.
Oh my gosh, there's more problems. Oh my god.